Okay, welcome back everyone to the afternoon session. So it's a great pleasure to present for Clemens. Ohio State will speak on string theory as applied to very classical algebraic geometry.
Thanks, Clemens. I wanted to thank the organizers for the opportunity. Can you hear me? To come and thank all of you for your patience in spending an hour listening to the mathematician who's trying to play a little bit in extra innings, as Warren Buffett said. So there will be no new mathematics in this talk. So this is an applied algebraic geometry talk. But the mathematics that is used goes way, way, way back, so far back that I think many of you in this room, how many of you know what a syzygetic tetrad is? Or a Cayley optic. You know that. So that's kind of where we'll start. In fact, that's the most fun part of this talk. And so when I got here and spent a day or two in the audience, I thought my slides are not in the right order to engage my audience. So now there will be a transition. There will be a short dive back into the 19th century at the beginning, because this is just great stuff. I mean, it's the stuff that I learned in early grad school, and it's the reason I did what's in this field. And please forgive any mishmashes of words on the slide. I go over them 8 times, but I still miss. So here is a quick run through things that this is the outline of the second talk. The second part of the talk. The first part will reappear, and I'll just sort of bounce over later in the second talk. That's kind of the organization. So we'll start with a special what the physicists call a DP9, what we call an irrational or a rational elliptic surface with an I5 fiber. So, and then we will track some symmetry breaking via that tape form, and that's what these string theorists like to do. We will paste 2 DP9s together, and we'll get what's called the heterotic model over a point on a base out of that union of DP9s. Oops. Yeah, I thought I pushed the forward button. There we go. We'll smooth that heterotic reducible model of the pasted DP9s to a take K3 surface over P1. And that will give us the fiber of what's called F theory, which is, the physicists would say, dual to the heterotic. We'll have an involution with finite fixed point set on B3. And the fixed point set will be disjoint from S gut. S gut, think K3 surface, well, think it is a K3 surface. Our elliptic fibration has a discriminant in the base, and that's S gut. And that's where all the action happens. That's where all the subatomic particles get together and whack into each other and create matter. You can tell I'm talking of the outer edges of my limit of physics by that sentence, but that's the idea. So then we'll take the quotient under that free involution. That'll give us an Enriques surface with an ample polarization, but the linear system will have two base points. And those two base points are where the elliptic fibers actually become cuspidal. And that's going to be where what are called Yukawa couplings take place, where first the cusp goes to a E8 singularity, right? And then we'll do roots by tangents, something called Z4 symmetry, which we all should like because that's in all the string theory to avoid proton decay. And if proton decay was not under control, there would be trouble, right? Or we wouldn't be, that's all. We'll show that we have three generations, meaning three families of quarks and leptons. We'll show that we have one Higgs doublet. These are just statements about cohomology, as you'll see later on. This Z2 action that we just talked about to get our Enriques surface will wrap a Wilson line, which will be the final step in getting to the standard model from E8 symmetry as when we began. And then we're, Stuart Raby, my physics colleague, and I are looking for help because those 2 points that I was talking about give an opportunity for a new way to construct Yukawa couplings, but I don't know the physics and he doesn't know the mathematics enough. We need help.
Third person.
Huh?
Need a third person.
Need a third person who speaks both English and French. Yes, right. And so there will be a plea for if anybody knows. And then the other thing we need is some computer algebra technical program design. just to do some high school algebra, but a lot of it. So the two sources that I indicated in the abstract, one, well, their genesis is Igor Dolgachev, who all of us should thank for writing a book called Classical Algebraic Geometry, which preserved in modern form all that 19th century stuff we're going to dive into in a minute. Part of the reason I lingered on the outline was my sense is, because it always happens to be, we never get to the end of the slides by the time the hour's up. So you'll see me at some point cut to the conclusion slides at the end. And so I wanted to give a good sense of where we're going. So the space we'll be working in now this is just the pre-talk, the space that we'll be working in is B3, simple thing, which is, I could use this, right? Yeah, so our S gut here will be in a B3, which is simply the product of P1 with a degree 2 del Pezzo surface. The thing, so that's two-sheeted covering of P2 with a quartic branch curve, and has the lovely property that's going to be crucial for us, that the roots of E7 are simply the kernel of the homology projection from H2 of the B2 to H2 of P2, right? So super important. This particular family of del Pezzo, if we polarize it with the anti-canonical bundle of B3, that gives us a Neff and big divisor. Oops, I didn't mean to do that. That gives us a Neff and big divisor, but the linear system has two base points, and that is the same thing, the same property as that a certain invariant of Enriques' surface Neff and big divisor has value 1. And that invariant is, you look at all of the H2 that is square trivial, so isotropic, and you take the minimum of the intersection number of those cycles with the polarization absolute value, that's an integer, the minimum of that over all the isotropic gamma, if and only if that is one, the linear series has two base points. That's the, I listed two references in the abstract. That's the most important piece of information I got out of the first. Any questions so far?
What is the definition of B3 check?
Of B3, that's the quotient of B3 under the involution that I talked about with finite fixed point set. Yeah, there will be a lot of quotients, and a C will always indicate the involution, and the subscript in the C will always indicate domain and quotient. So anyway, so as I mentioned, it's those two base points that are candidates for the sites of computable Yukawa couplings, the place where the quarks, the leptons, the neutrinos, et cetera, interact, facilitated by the Higgs boson, which is a H1 class. Yeah.
Is there a misprint there because those two things look identical? There's like maybe X1 and X2 or something like that.
Oh, that's what is one of the things that I. Where does that?
In the 2 points there. Line -4.
Fourth line from the bottom.
4 slides from the bottom. Absolutely. That's one of the screw ups. Yeah. Right. Okay. So Dolgachev kind of 30 years ago almost said that the family of the quartic curves that is the branch locus of the del Pezzo over P2 has a distinguished even theta characteristic. And if you tensor the canonical bundle of the quartics, which is just linear, with that theta characteristic, you get a morphism to P4. The graph of that morphism produces in the T cross X space a three quadrics parameterized. So what's called is it a net or a web? It goes pencil web net. No, pencil net web. A net of quadrics in P3. They're symmetric. These equate. It's each of the quadrics is presented as a symmetric matrix. Okay, and the determinant of that thing is the original. So it's a linear determinantal presentation of the 4th degree plane curve. that okay?
Distinction of the theta characteristic.
I'm sorry.
What distinguishes that theta characteristic?
What is the?
You say that this theta.
Okay, yeah, that's a little bit of a cheat. What they showed was that you have two spaces, the moduli space of plane quarks and the moduli space of plane quarks, comma, the even theta characteristic. Those two are birationally equivalent. So that it's in that sense that I mean that there's a distinguished. It's distinguished, but you don't really know which one you pick.
Distinguish between different quartic.
That's right. Yeah, it will turn out that we're going to have a one parameter family of the quartic curves in the setup, and that birational image of one of those quartics is another quartic in that same one parameter family. It just jumps somewhere else on that. Okay. So a two-dimensional P2 of quadrix has a base locus. The base locus is 8 points. If you write down the 8 points, and you project from any one of those 8, that takes you to a P2. That's not the P2 that we talked about before. It goes like this. The element of that P2 we talked about before is a pencil of quadrix in the P3 containing the octad. You project the intersection of two quadrix from any one of the 8 points, you get a P2 with 7 marked points, namely the other 7 marked points on the intersection of the two quadrants. So you have a cubic in the plane through 7 points. That you blow up those 7 points, and that is your del Pezzo of degree 2. So it is a 2-sheeted cover of our original P2 double dual. So it's our original P2. So that is the 2-sheeted covering, B2 over P2 branched on this smooth quartic curve. Any questions on that? This is the kind of stuff I just love. So how do we get the 28 bitangents to every smooth plane quartic curve? I never knew any of this stuff, even though I'm old enough, I should have learned it. I never did. It's all new to me. Anyway, you take 2 of those 8 points, you go back to that graph, the linear combination of quadrics, you stick in the 2 values of the base points. So what do you get? You get a linear form in T1, T2, T3. There are 28 ways to do that. Those are the equations of the 28 bitangents. How many of you knew that? 0. That's why Dolgachev wrote this book. We should all be incredibly grateful to him for that. Okay.
Is B3 just around the corner?
Is
B3,
B3 is just around the corner.
right?
This is the B2, and the B3 sits over it. And we got the B3 by smoothing. We had 2 DP9 things crossing. We smoothed it. Okay, that gave us the B3. And
Is the second Bennett number of B3 8?
Let's see, the second number of B3, I guess, should be 8. Yeah. Okay. Let's see. So now we specialize to a our B2 to a 1 parameter family of quadratic plane curves. The parameter is alpha, and these are, it's the most symmetric 1 parameter family of plane quadrats that has been studied in all possible ways. That's what Dolgachev told me anyway. So it has a huge, well, not a huge, as we'll see, the symmetry group of this is the automorphisms of the cube, including the reverse, the orientation ones. And then to Rob's question, alpha changes when you go in this map from a quartic plane curve to quartic plane curve, comma, even theta characteristic. And I mean, these are just because it's so tightly arranged. Those quartics are smooth, except that plus or alpha equals plus or minus 2. So it's high school algebra to relate or to calculate the bitangents for this family. And I'll just skip through that because, yeah, anyway. You do some algebra and you see where that 0 and if C's satisfy that equation, there's a relation between the C's and the alphas. And that gives us the C's for the determinantal presentation of our F alpha. Okay, and let's see. So I skipped over this slide, but that's the symmetry group of now. This is the symmetry group of the plane quartic plus one more generator, which is the reversal of the orientation, the reflection through the center of the cube. This I liked what happened in the last talk yesterday when the speaker broke up the cube into these things. This is a picture of it. The Cayley octad, which is the 8-point base locus of the family of quadrics, are the 8 vertices of that cube. And so but they're the 8 vertices of that cube in a special way. Yeah, and this is what I just said before. Yeah, well, in the case of our special quartic now. So, I mean, you could use the first 4 points to set your coordinates, and then the second 4 points appropriately ordered, and it will not matter how you order them as long as you get this. You get this diagonal, and that's the diagonal elements are the only variable in this. Okay. So pretty obviously from the equation itself, the automorphism group of B2 is the signed 3×3 permutation group, plus or minus 1. 1 plus or minus 1 in every row and every column. And the action is simply what you'd expect it to be, where the important thing here is if you want to change the sheets between the 2 points over each point on the plane, that's controlled, as you would imagine, by the determinant of the sign permutation. Full symmetry group has 3. For us, that S4 is going to be the Weil group, the A4 Weil group. And the S2 is, as you guess, the reflection through the center of the cube. And last but not least, it's pretty obviously from the equation itself, the semi-direct product of permutation group on 3 letters and plus or minus 1 cube. So this match is blue vertices. Yeah, we have the 2 tetrahedrons, right? And with the property that each tetrahedron, no tetrahedron contains an edge of the cube. So we think blue vertices paired with red vertices, that's the central involution of the cube. Bitangents are vertices of the cube. The syzygetic tetrad is a set of 4 odd theta characteristics whose product is twice the canonical divisor. That's what syzygetic means. So the bitangents 28, fine. Cayley octave generated by 1 even theta characteristic that is invariant under the automorphism group. 4 partitions of the 8 points are the other 35 even theta characteristics. One of which, of course, is our blue-red partition. And this is going to be essential. The Cayley octad places, if you will, well, I'll say it this way. So E7, the roots, or all of the theta characteristics are pairs of vertices, the odd ones, and 4 partitions, the even ones. If you do +1/2 -1/2, let me go back on that. If you do, if you look inside of E7, and it has a maximal rank subgroup SU8, and so that if you take the fundamental representation of SU8, then that will set up the coordinates for that correspond to the 8 vertices of the cube that correspond to the 8 points of the Cayley octad. And once you have those axes for the fundamental representation of SU8, then by taking pairs of plus or minus pairs of vertices and 4 partitions of those basis vectors, okay, you get all the roots of E7. And if you take the increased number, you get all the roots of E8 placed in the standard orthogonal space. So you get the orthogonal space for the roots of E7 and for the roots of E8 that is being fixed or distinguished by what we've got so far. Okay. We're going to want, in order for rotation around the T3 axis, that's going to act on our syzygetic tetrad, and that's going to give us our Z4 R-symmetry that gets rid of proton decay. Our syzygetic tetrad of on theta characteristics is a top red pair, a top blue pair, a bottom red pair, and a bottom blue pair. So the rotation around the T3 axis will just interchange those. Okay. And that's the end of the first part, and I'm probably, yeah, so we're gonna have to speed through the second part. Anyway, any questions at this point? So, do people like this stuff? I love this kind of stuff. Maybe it's like my parents used to love a certain kind of music and I couldn't stand it. Anyway, it's back when algebraic geometry didn't have such a high ticket price to get into. Yeah. All right, so now I need help.
So we're just switching to level talk, right?
Yeah.
Here we go. Okay, so we're going switching to this one.
Yeah.
Okay.
Okay.
If you need to go faster, you can use these buttons. So
Oh, I see. They go faster than this.
they're just easier to. Oh. Okay. There we go.
Yeah.
Okay.
Okay. So, yeah, this is what we saw at the beginning, but hopefully now with a little more context. Okay. So the starting point of the construction, at least the way that I think of it, it's called the heterotic side. And what we start with is a dp9, rational elliptic surface, given by the Tate form. So this is a form. There's its equation. It's parametrized by P1, right? It's a family of plane curves. The plane curve coordinates are W, X, Y. And the parameter is A0 and A1. If you just make all the other coordinates 0 and set A0 not equal to 0, you get a one parameter family of deformations of the cusp that when you resolve, there's the one parameter family, when you resolve it over lambda equals infinity, you have the E8 Dinkin diagram. You have the little exceptional curves give you the E8. So we think of cuspidal point. We're going to have two cuspidal points, those 2 points where all of the sections vanish. And then we're going to do a blow up and blow down of that. And this pencil will get squashed to a single point. So the way we say that is that this whole pencil is occurring up in this spectral divisor over B3, over a single point on B3, and then same for the other. Okay, so let's speed up. So there are two views of the tape form. One is, gosh, sorry. The first one is, it's the deformation of the cusp, okay? Parameterized by the A dot up to A5. Well, A dot and then A2 up to A5. So that's the first way. By the way, I should mention, I think I wrote it wrong. This tape form is arranged so that the main component of the discriminant of the family of cubics is given by z equals 0. So I want to go back. I didn't comment on number 2 here, that if you, in the tape form, set W equal to 1, so you take away infinity, divide by 8�6, and change course. If you rescale, the tape form becomes this. And when you look at it that way, that's a deformation of the E8 singularity to an A4 Duval singularity. So so we want to think of it in 2 ways. You start with the cusp, and then also you can forget that and start with the E8, and that's affected by number 2 here. And so if I parameterize the cusp by those t's, then the resulting equation is looking at where that family of cubic curves, the total space has singularities. And the places where it has singularities are parameterized by this, or where it can have singularities, I guess, are parameterized by what you get by simply restricting the tape form to the parameterized cusp. So over our DP9, make a long story short, we have 2 E8 bundles. One of them is the visible universe. The other is the hidden universe, dark matter and energy. If you restrict this either of these E8 bundles to one of the curves in the dp9, it becomes flat, totally reducible. So it's parameterized by 8 points on that base curve. And you do that for both of two dp9s. You take two dp9s that share one fiber, and you get 8 points on an elliptic curve. Gives you, it's the same thing as 8 flat line bundles on the elliptic curve. Is syzygetic the same thing as mappings of the fundamental group of the fiber into E8? Is the same thing as flat complex bundles on the elliptic curve. Is the same thing as 8 marked points, is the same thing as a pencil of cubic curve with 8 fixed points. Is the same thing as an elliptic fiber del Pezzo dp9. The fact that the discriminant of our tape family has a Z5 factor says there's an SU5 substructure to that bundle structure to that SU to the E8. Later, when we do the involution, that is incorporated by sending each of the 8 marked points to its negative on the elliptic curve. That's the same thing as taking the complexified E8 to the complex conjugate of the complexified E8. That's, of course, not holomorphic, but our quotient must incorporate that because that holomorphic one form on that elliptic curve is going to have to go to its negative under that, because the holomorphic 2 form on S gut goes to its negative, because you get an Enriques surface. So those two negatives mean that our quotient is Calabi-Yau. That's the. Okay, so we're going to skip over tons of stuff. Yeah, there's singularities. We're just going to go. Oh, yeah. Okay, so the symmetry breaking is cuspidal symmetry, E8 Duval singularity. Then as you add more terms to the tape form, the singularity associated changes, and what it looks like, you're adding U1s and decreasing the rank by 1 every time you add a coordinate to the tape form. Okay. So that corresponds to, of course, peeling off 1 by 1 the right-hand roots of E8. The increasing number of terms has 3 effects. They reduce the symmetry of the model, E8, E7, E6, SO10, and SU5 gauge. So they allow the commutant of that decreasing sequence to be an increasing sequence, right? That goes from nothing to SU5 Higgs. The sum of SU5 Higgs and SU5 gauge is a maximal rank subgroup of E8. A moving U1 we're going to see in a minute, corresponds to a second section of the DP9. Okay, so we're almost out of time, so I'm going to go really fast. That corresponds to that extra section, gives us a factorization of that rescaled tape form, signifies a decomposition of the SU5 Higgs, opposite one, into SU4 cross U1. Okay, so now you just put all the DP9s and unions of the DP9s together, and you come up with something fibered over our B2. So we have the union of 2 DP9 bundles over B2. Their intersection is the heterotic Calabi-Yau threefold. Now, I have a old man's tremor that I inherited from my dad, and it's giving me trouble right now. Anyway, that if I take the union rather than the intersection, that is a singular Calabi-Yau fourfold with the Calabi-Yau threefold as its singular locus. And then we simply deform that A-axis P1 that we had before, the 2 copies, into a single single P1, and there's the discriminant of the family of cubics, and we smooth, and we forget about the deformation parameter because we could make an x1 and an x2 that'll work restricted to any of those p1s, and so forth and so forth. And let me, I'm going to need just a couple of minutes if I could. Essentially, the way we make our Enriques is we first take B2, we take 2-to-1, two 2-to-1 branch covers and take their fiber product. In this, oh man, yeah, I've discovered I'm too old to do this because I can't keep it. Anyway. You keep taking fiber products. The new arrow that is created by taking fiber products is branched along the intersection of the branch locus of the two original maps. You do that a few times, you end up with a S-got that misses the branch locus entirely, so that's what gives us our quotient. And now I will go all the way to the end and just say that this model, when you go through it, and this is all the stuff that we're not going to be able to talk about, that model, when you go through it, ends up with all the computations of the Yukawa couplings taking place on a P1 cross P1 that by blowing up and blowing down gets you to our S got downstairs. So the computation of the Yukawa couplings gets reduced to something extraordinarily simple. But the algebra is too much to do by hand. So we're looking for someone who could guide us through that. And then we're looking for someone to translate who could tell us what those high school algebra computations should be. And with that, we end up with 3 generation, 1 Higgs doublet, no vector-like exotics, then 4 R-symmetry, all Yukawa couplings calculated in the spectral variety over the 2 base points. Computable. Thank you very much. Say again.
The slide with, put it back.
Yeah.